Hi everyone. This is the video on problem set 6 for econometrics, or what else is it called? Assignment 3, or problem set 6, whatever you want to call it. I'm gonna go through the questions right away, and hopefully my answers make sense to you. So let's get started. So first of all, for question 1, we have a child living in a particular school district, and we're going to let voucher be a dummy variable equal to 1 if the child is selected to participate in the voucher program. So if they do get the voucher, it's equal to 1. If they don't, it's equal to 0. And we're going to let score be that child's score, which is going to be a quantitative variable on a subsequent standardizing exam. Right. Oh god, got a bubble in my throat. We wish to learn about the effect of participating in the voucher program. So this is referred to as a treatment effect. Again, yeah. And we want to set up a regression model that allows you to measure the effect of the school voucher program on student performance. So because the voucher program is affecting, the score, the voucher is going to be the regressor and the score is going to be the response. So you can see here, this should be a good sample regression model. Okay, so if the child does get the voucher, they have beta 0 plus beta 1 for their score. Whereas if they don't get the voucher, it's just beta 1. There you go. So for B, let's say that less able children have a greater chance of being selected. So if children who have lower scores are selected for the program, then you get a reduced coefficient as a return to score. If, for example, we have children who are less technically academically minded when it comes to these kinds of things. Oh, sorry, I've just lost it. If we take on kids that are less academically minded, they're going to get lower scores, and the regressor is going to get pushed down. So it's going to be underestimated. Now, underestimation is essentially negative bias, and overestimation is positive bias. So, because we've underestimated actually what the regressor is going to be, it's going to be negative bias because we've underestimated. Okay? All good? So I'm going to have to cough. All good. So, suppose instead that the participation is completely randomized in the sense that a given child is randomly selected into the program, irrespective of the child's background. So children are just randomly selected to enter. Does the OLS estimator provide an unbiased estimate of the effect of the voucher program based on its design? They should be the same, necessarily, when it comes to both the average of the voucher group and the average of the non-voucher group. However, because the process is randomized, we may end up in a situation where those who have vouchers may have been randomly selected, and the random selection gave us kids who are necessarily smarter or kids who are not as smart. So because of the randomization, we can't be sure that both groups are distributed evenly in terms of skill. So it's not necessarily unbiased. Okay, there's always going to be about some amount of bias present, but yeah, when we're randomizing, it's hard to eliminate bias entirely. We also say here, suppose we collect additional background information such as family income, family structure, parents' education. Do you need to control for these factors? You can control. Do you need to control these factors to obtain Yeah. So here's the question: do you need to control for these factors to obtain an unbiased estimator? So you don't need to, but it would be good to. You wouldn't need to in two cases. One, your population distribution is the same as your sample distribution. So, for example, if I've just realized there's a random stuff there. Oh god. Yeah. Let me bring up my whiteboard. So, if you look here, okay. Imagine if you would, that the population distribution looks a bit like this, okay? And the mean exists here, where something occurs. But the sample distribution may look like this instead, okay? Now, is the sample distribution representative of the population distribution? No, it's not. Because they necessarily have different means, don't they? However, if they do overlap, something like this, then we can be sure that the estimator is representative of the population. Okay, but if they don't, it's uncertain to be sure. However, if we fix factors in the sample in order to make these overlap, such as controlling for certain factors, we can just eliminate this problem. Okay, so that's one case where the population and sample distributions are similar, and then the other case is when you have basically a constant. Okay, so for example, imagine if every family has the same income. Okay, then I wouldn't need to control for it because every family is included within that group, so I wouldn't be able to control for it. However, it would be good to control for the other factors because you generally can say like, okay, given holding this constant, basically the ceteris paribus assumption, what is the effect? And then sometimes that is useful, but it is not necessary. It's useful, not necessary. Even if the OLS estimator is unbiased, would there be situations where you would still include family background variables in the regression? We could actually include family background variables to determine the effect of certain familial factors on a child's score. So for example, does a family's income affect how high a child scores in their standardized test? Maybe they get more study materials and stuff like that. Or does living with one parent versus two change the child's score? That would be useful. However, we may not necessarily want to include those because there's simultaneity bias, which is where we have two factors, one response, one a regressor, that are both affected by one thing. So for example, the child's score and the parent's education levels could both be affected by their shared intelligence, which is a sort of amount of simultaneity bias. Or you could say that the family income and the score are affected by socio-political factors. So simultaneity exists there. So it may not be perfect to use these familial factors in the regression because of the simultaneity, but it's useful if we want to determine the effect of these factors on the score. So there's that. We also have the randomized program is to be put in place, but there's attrition, which is that some children drop out of school and never complete the standardized test. Should we be concerned? Well, yes. Now, there's one thing that we can just say right off the bat is that we're going to have reduced data, which is going to reduce the validity. Okay, reduced data, no one really wants that. But the important thing to note is that who is dropping out? Because often children with high scores and are doing well academically don't often drop out. It is often children who do badly who drop out. So we're going to have a gap in data at the bottom end of our sort of scale when it comes to things. So, for example, if we have sort of this whole distribution of points, we're going to miss some here, okay? So we're going to have to, because of that, interpolate the fitted values for our regression, which is going to be less accurate because we don't have data for that point, okay? And if we don't have data, it's going to be harder to make a fair assumption. So it's difficult in that case. What's also going to be the case is that our regressors are going to be estimated higher than they are. If I lose lower scoring students, my regressors are going to be higher than they realistically are in the population. So that's not good either. Okay, that's pretty much question one. I think it's a lot just of explanation, but I think it's pretty good. Now on to question two. Yeah. Oh, by the way, I've just had this open. I haven't really been using it, but it's here. So there's that. So for this one, we're going to use crime 1 data, which is on the Moodle page. If you go all the way up here, you go to resources and you go to stata datasets, you click in here, there it is, crime 1 data. Oh, death data. Interesting. I don't know what that is. So we got the variable descriptions here. This is the criminal and labor market histories of California men born in 1960 or 1961 with at least one arrest prior. Okay? At least one arrest. So, what we need to do, and what the question asks us to do, is to estimate a linear probability model that explains whether a man was arrested in 1986 by his prior criminal and employment record, and it's given us the list of variables to use. So, should we trust the standard report here? So, first of all, to create a linear probability model, our response variable needs to be a dummy. And whether a man was arrested or not is not a variable that currently exists. However, we currently have number of times arrested. We can actually use this to create a dummy. So okay, I'm going to go through how you would do this. So I'm going to type it in. I'm going to show you how it happens. I've pressed on the death data. It was just so tempting. Yes, so here's my window. I'm going to show you how it's done. So, oh god, come on now. There we go. So, we have our thing here. So now what I'm going to do is I'm going to generate a dummy for the number of arrests, okay? So, what I'm going to call it is I'm going to call it dummy nar86. So we're going to say generate. You can also say gen, but I'm just going to write out the full thing. Generate dummy nar86. And I'm going to set every value equal to 0. So I've generated the dummy. And now what I'm going to do is I'm going to set the dummy to 1 if someone has committed a crime. Or, in the terms of the model, if nar86 is larger than or equal to 1. So we can write this out as replace dummy nar86 with 1 if nar86 is larger than or equal to 1. You should see 755 real changes made, and we're done. So now we can put this in our regression. So we're going to do regress dummy nar, because we remember we need to make sure the response variable is a dummy in this case. Then we can add in all our other stuff. So we're going to add in PCNV. We're going to add in, what else? Yeah, we're going to add in AVG-SEN, or average sentence. We're going to add in total time. We're going to add in prison time, 86. And we're going to add in QEMP, or the quarters employed for the year. And putting this in, oh, hold on, let me expand this out. That's a bit of a bad thing. Sometimes when you compress data down, it doesn't really display the values correctly. Let me try that again. Ta-da! You should have something that looks like this. Okay? Something that looks like that. You should have, yeah, so this constant, this PCNV, that kind of thing. Okay? Alright, so now we've got our sort of thing here. Now, do we trust the standard errors? We shouldn't. I think this is mentioned in this one here when we talk about linear probability models. So look, by the way, slides in this week pretty accurate, so go for them. Yeah, where is it? Here we go. So fundamentally, we can see here that the problem is it's violating, what is it? Is it violating heteroscedasticity or violating homoscedasticity? Yeah, okay. It is heteroscedastic. Yeah. Hold on. Yep. Yeah. So the problem is here that because MLR5 stipulates that the variance u given x has to be a constant, and we're showing here that it's not, then MLR5 is broken, which basically means that the standard errors can't work because standard errors rely on the fact that the variance of the error term given all the x's is constant. And if it's not, then we can't really trust standard errors. We also can't trust t-statistics or f-statistics because they're based on standard errors as well. So, no, don't trust the standard errors. That's basically the big deal. What is the interpretation of the intercept? So, it's good to write this out in longhand. Okay, so this is 2b. This is good to write this out in longhand. So, let's consider it. So this is the probability that a Californian man who was born in 1960 or 1961, who had at least one arrest prior, the probability of him being arrested this year, given that he has had no prior convictions, okay, has never served prison time at all, so these three turn to 0, and has not been employed for the entire year. That would be the probability. No convictions, no prison time, not employed. So basically an unemployed guy in California who's had at least one arrest before. That's the probability. Try to speak out it in words, mostly just because it becomes easier to understand. Interpret the effect of time locked up in 1986 on the probability of arrest. So we're going to be looking at p time 86 because that is the time locked up in 1986 on the probability of arrest. And we can see that the regressor coefficient is negative 0.02, which would say that for every year I am locked up in 86, the chance of me being arrested declines by about 2.1%. It looks small as an effect, but it's going to work in a larger aspect. Think of it like if I times this by 12, okay, if I times that by 12, so 0.0129666 times 4, you can see that it's going to have like a 26% change. Okay, so I'm going to have a 26% drop in my chance of being arrested. So it does look small, but it affects cumulatively because the maximum value this dummy can actually take is 12 instead of just 1. So that's good. Set all explanatory variables to 0 except for p time 86 and compute the predicted probability of arrest in 1986 for a man who was locked up all 12 months in 1986. Does this prediction make sense? So you can calculate this and you would get the value 0.1770186. Okay, if you just set everything to 0 except p time 86, which you'd set to 12. However, you would expect it to actually be 0 because if you're in prison, surely you can't be arrested. Now, technically, and I don't know if the people making this understood this, but you technically can be arrested while in prison. For example, if you commit a murder while in prison, technically you can be held under detention. I am assuming in this model that all the people who are currently in prison cannot be arrested. I am assuming. Okay? But I'm saying it could be a possibility. We could interpret this coefficient, 0.1770186, as the probability of being arrested while in prison, but I doubt the people who made this data set considered that, so I'm going to go with the fact that it's just not possible. Okay? Next, we test whether average sentence and total time are jointly statistically significant. So we can see in our regression that they both have quite high p-values. This one has a 34.4% significance level. This one has a 65% significance level. So we're going to test, are they both statistically significant at the 5% level? Now we can do this just by writing the command test. Okay? Test will perform an f-test with both variables, and it will give us a significance level. So here, our significance level, and I will do this now actually, because this will be easier to show you. Test AVG sentence, or average sentence, and total time, and you get this, and you get, if you can see that, or you can maybe see it better here, the p-value given to f is going to be 34.6%-ish. Okay? So that shows us that it's far too high to be significant at the 5% level. If it's above, it's just not significant. But if it's significant enough to reject the null. But if it's below, it is. Okay? Given it's above, we can't reject the null. So it's quite possible that both of these coefficients can be 0 at the same time. And yes, we should worry about the validity of this test because it's an F statistic, and F statistics is based on standard errors from the model, which we've already shown are not valid because they break MLR5. Okay? So we can say that maybe this F statistic test isn't completely valid. Next, and finally, actually, calculate the predicted probabilities and verify that all fitted values are between 0 and 1. What is the smallest value you observe and the largest? Now, this was covered in the... Yeah, it was covered in the slides somewhere. Here, yeah. On slides, is this 20 or 21? It's 20, or it's here. Basically what you have to do, and it's really unintuitive, but deal with me, is that the predict command, okay, essentially you use a random variable, and that random variable is going to signify the fixed values, okay? And once we pick that random variable, given that we've already computed the regression, it's going to represent all the fixed values. You can just do it by itself. You can do comma xb afterwards, like I did, or you can just do this. It really doesn't matter. But basically, say predict and put in something random. I used just x. The point is that it doesn't show up in it can't be anything we've said before. So just use something random. So I said predict x, xb. Then what we're going to do is we're just going to summarize the fitted values and take a look at all of them. So this is going now, x now represents all the fitted values, and we can see when we look at x that the minimum fitted value is going to be 0.0066431, and the maximum fitted value is going to be 0.5576897. That is what you should get. So these are the smallest and largest values. Now you technically can say that, well, the model doesn't work because if I put in this and that, it doesn't work. But we're not talking about the values we're putting in. We're talking about the fitted values of the model, which are different to breaking the model itself. Okay? So this is generally what they want you to do, mostly because it was mentioned in the slides. So better to do that than to not. Okay, I think that's everything. Hopefully that was helpful. I'm going... Oh, and also, little announcement. I'm running my quant catch-up group tomorrow from 1 to 3 p.m. We're going to cover all the week 6 content, more basically going over the slides, making sure everything's very intuitive. And I'll cover this again for everyone who wasn't able to, watch this video fully and stuff like that. But yeah, I didn't really touch on the Chow test, but that wasn't really useful. Okay, well, I think that's just it for me, and I hope you guys have a lovely night, or day, or afternoon. Have a good time. Okay, bye.